Good morning, everyone. My name is Shinpei Kato. I was in information science until last March, but I moved to University of Tokyo, but I still belong to Nagoya University in the research project. So I'm still working on today's topic, which is about autonomous driving. So because I believe that this course only has 40 minutes, so I'm going to give you some intuition and a brief summary of how we can build up an autonomous vehicle from scratch. Scratch means that if you want to start such kind of thing tomorrow, then how? So before I give you a technical details, let me briefly introduce myself. So I was working on computer science, and I was in Carnegie Mellon University for 2.5 years, and I saw some interesting project on autonomous driving. So CMU, Carnegie Mellon, was one of the most popular universities in this domain, and it was pretty impressive to me. So when I came back to Nagoya, I decided to start a similar project to CMU. And I'm also working on supercomputing or hardware, LSI, and operating systems, which is all about the computer science course. And I joined Nagoya University 4 years ago, and we started this project. And if you go to National Innovation Complex, which is over the crossroad, and you'll see a few vehicles that we use for the research project, and most of them actually modified to drive by themselves. For instance, for me, what I'm interested in is, for example, to bring supercomputing technology to the vehicle from, say, huge data center, because today's technology, which can say reduce the size of the computer or reduce the cost of the computer, so that typical vehicles can afford to accept such a high performance computing power. This is my research interest, but basically as a university, we are promoting the project on autonomous vehicles. So we have a lot of collaboration, for example, TMC, Denso, and so on, which are and all supporting one of the biggest academia industrial project of Nagoya University. And now, since I moved to Tokyo, I made a kind of extension to my work, which can also support autonomous vehicles by, say, artificial intelligence, for example, because supercomputer has a lot of computing power to produce intelligence by collecting data and so on. Okay, so today's topic is about an autonomous vehicle, and this is what we have demonstrated 1 year ago. This is on a public road, and there is no closed environment. So it's open environment, and there is no, say, staff vehicle. Every vehicle around our vehicle is actually, they just drive in the city. So there is no restriction on this experiment. And we are driving at approximately 50 to 60 kilometers per hour. So if you drive at that speed, this is almost a kind of realistic assumption that we can show that an autonomous vehicle can coexist with the standard vehicles. And since I'm not a vehicle expert, so I don't really get interested in building up a specific vehicle, but we are providing some prototype vehicle in order to show our software techniques and sensing techniques and so on. And this is an example of the case where we only have two sensors. One is laser sensor on top of the vehicle, and the other sensor is a camera on the front window. We only use these two sensors, and this is one scenario that we can realize by only a set of two sensors. And since we are driving 50 or 60 kilometers per hour, we can just bypass the surrounding vehicles. And we have been working on this project for a couple of years, and now the system is becoming a platform. Platform means that if somebody else outside of our project want to use the same system, then they can just use it. Oh, by the way, so this time, do you know him? He's a governor of this prefecture, Aichi prefecture. And so we made a demonstration for him, which means that the vehicle is at least complete in a quality that we can provide him a lift. So sometimes to take a real person to the prototype system, it's pretty hard to prepare, but our vehicle is, in a sense, complete in a quality that a real person can just ride on. And now this platform, this system, is getting broadened and broadened. And they are using our software, using the same set of sensors, and do the same experiment in Kyushu. And we didn't support it at all. Just they downloaded our software. Well, we supported a little bit online, but basically they built a vehicle by themselves and bought the sensor and installed the software, downloading from the website. Then they could do this just for 3 days. They needed only 3 days to make this demonstration. And another case is that this is Yamaha motors, not on the public road, but in off-road course. But again, the same system, laser sensor on top of the vehicle, plus the camera. Then they can do exactly the same demonstration as what we did in public road. So this means that if you have a kind of platform open to the public, then now a lot of, say, those outside of the project can also build an autonomous vehicle from scratch. We didn't support it at all again, just we support a little bit online. So basically on the spot, only the project staff from that company just built the system. So autonomous vehicles are getting more and more practical recently, and some of the products are, I believe, showing in the market in a very near future from automotive makers. But they are basically for highway, which are very different from what we are doing, because we are doing on public road in the city, which is very different environment from those the automotive companies are targeting for. We are more close to Google. So Google is making a huge leap to realizing the autonomous vehicles in a city. So we are, what we are doing is pretty close to Google rather than automotive makers, since we are targeting a public road in the city, which requires a lot of skills and techniques from learning from real world. So in that sense, what I'm talking to you today is relevant to what you are studying in this program. So again, I don't want to make a technical detail, because I only have 40 minutes. But I can show you in 2 years, almost 2 years and a half, how we could build an autonomous vehicle from scratch. So what do you think? What we need first to do is you need a hack to the vehicle, because if you buy a vehicle from the market, it doesn't have an interface to connect to the computer. So what we have to do first is to make an interface between the vehicle and the computer. And fortunately, we found a small company a few years back which can make such a modification and we bought a vehicle from them. And that modification, for example, is applied in car network, and they slightly modified in the car network so that they can send a signal to ECU is it's a computer in a car. They can send a signal directly to those ECUs from the computer that you put on later. So by passing actually the real car network, then the car actually is being able to be controlled by a plug-in computer. So this is what you have to do first, or otherwise any software technologies that you build cannot be applied for the vehicle. So this is what you have to do in the first stage. And since now you have a computer in the car which is connected to the vehicle, so for example, you can do this. There is no intelligence in the car, but you can actually remote control the vehicle from the computer. So it's not driving autonomously. Somebody is actually controlling the vehicle from remote, because now it is connected to the computer. If the computer says change the angle to 60 degrees, then the hand steering is actually changed to 60 degrees. So now the vehicle is able to be connected to the computer. So what we have to do is to put computers. Not a stupid computer, but because we have to make a difficult decision or a difficult perception, so the computer must be somewhat powerful. So in the first prototype that we made, we put desktop computer in the car. But now we actually made it a small into laptop now. But first we used a desktop computer. And even though you have computers, still you cannot make them autonomous because the car cannot sense the environment. So you have to put sensors. And what sensors are the best? This question is very difficult because nobody knows what set of sensors are the best suited for autonomous vehicles. So as a university project, we buy as many sensors as possible and to test what sensors are working and what are not. For instance, they are laser sensors scanning on top of the vehicle to sense distance information, ranging information. And this is GPS, not very same as what we have in your smartphone. This is more accurate. And we have camera, and this is also a laser sensor, but a different specification. So we have many sensors, and we test them, how they work, and what sensors are good for autonomous driving. That's what we want to know. But still, you cannot drive autonomously in a city. So you have computers and sensors, but still you cannot because you don't have a map. So you need a map to drive in a city. On a highway, you don't need a map because you can just keep your vehicle along the line. But in a city, since you may not have lines, depending on the condition of the road, so you need a three-dimensional map. So three-dimensional map recently means a lot. Somebody may think this is 3D map. So this represents the shape of the real world by three-dimensional coordinates. So this is not a picture. This is a collection of points at so much higher resolution so that it can look like as if it's a picture, but it's not a picture. It's a collection of points. Since it's a collection of points, it actually represents a three-dimensional shape of the real world. But this is not sufficient yet because we only know the shape. We don't know what they are, right? So if you are human, if you look the picture or if you look at this map, you may be able to understand, okay, this is a building, this is a crossroad, this is traffic light and so on. But computers, they don't understand so much quickly. So we have to embed as much information as possible, especially static information, because the computers don't need to understand dynamically such static information. So you can just embed the information beforehand. What's the static information? which is, for example, crossroad, or how the lanes are connected, for example, or the location of traffic light. Well, of course, the buildings are also static information. So these lines, vector lines, represent information embedded in 3-dimensional map. So now we have 2 layers. One layer represents the information about the road, and the other layer represents the shape of the real world. By coupling 2 layers, then now we often call it 3D map, or high definition 3D map. So how we can use the 3D map? There are many ways actually that we can use 3D map for autonomous vehicle. So I'm showing a couple of scenarios that 3D map is becoming a very powerful tool. One is that, so this is a sensor attaching on top of the vehicle, which can detect the range information, distance information around the vehicle. This is also a collection of points. It looks like it's just a few circles, but circles are composed of a lot of points because they are also distance information. So it can also represent somewhat the shape of the real world. So now, because 3D map has a shape and sensing information also has a shape, so we can make a scan matching of 2 different data sets. Because they also represent the real world, they also represent partially the real world. So there must be some coordinates which can match the shape of the sensing information within the map, because they both in the real world. So we actually do this matching in real time. When a sensor information coming along with the vehicle, then we do this matching. And sensor information arrives every 100 milliseconds, so it's a 10 hertz, working at 10 hertz. So every 100 milliseconds, we do this matching, sensing information and map information, and localize the vehicle. And this arrow shows the direction and the position of the vehicle. And its accuracy is within a few centimeters. So this vehicle knows where it is driving within the map by a few centimeters accuracy. And surprisingly, so this grayscale represents the 3D map. And each point already has, so it's a collection of points as I told you before. So each point already has a GPS information. So this means that since this vehicle knows where it is driving by a few centimeters accuracy within the map, which means that he also knows where it is driving on the Earth, because it has the GPS information embedded in 3D map. So this is one of an example that a 3D map becomes pretty powerful tool. So this laser sensor actually is also very powerful because it can also work in nighttime. So imagine that you have a camera, but camera, unfortunately, well, depending on its specification though, it cannot work often in nighttime because it doesn't really see. But laser sensor, it's not really affected by the around environment of the weather or time condition. So it is useful for us because it's almost 24 hours working. And recently, this kind of laser sensors are showing up in the market with huge size of cost down. So the sensor that I showed you, it's almost a 50K US dollars. It's very expensive. However, these sensors, it's actually less than, it's almost 10K or less. So actually, this sensor can be purchased at a $7,000 or $6,000. It's still expensive, but it's affordable very much for the research project. And basically, we can do the same thing. So we don't really have to use the high-spec, expensive sensors now. You can instead purchase the low price sensors and do the same thing. But we have to evaluate what's the accuracy of localization. Is that really the same as what high spec expensive sensors can provide? So we don't know. There may be some degradation in accuracy of localization, so we have to evaluate in a research project. So for instance, if you know your location by a few centimeters, now, for example, you can make a new, for example, navigation application. So this is 2D navigation that you can download from smartphone market today, but we are building a 3-dimensional high accuracy navigation because we know where the vehicle is driving on the earth. So instead of just showing on top view with kind of approximate information, we can provide high accuracy information, which lane and what location within the lane you are driving. We can show that accurate information to the users. So it's a new application which is enabled by autonomous vehicle. So, and you may wonder how we can build a map. It's actually difficult, and we need a company support. But if you are fine with a rough map, then you can just build it yourself, because you know the location of yourself at high accuracy or at a few centimeters accuracy, and you have the sensing data. So if you keep saving this sensing data, because you have your location very precisely, and you also know the pose direction of yourself. So if you keep saving data, then as you drive, the map is actually building because the data is accumulating. And if you drive for example, 1 minute, almost 1 minute, then such a small space, in such a small space, you can just build a 3D map. So this is often called simultaneous localization and mapping. In robotics, we often call it SLAM. So I believe robotics domain is one of the core fields that can promote and facilitate the innovation of autonomous vehicles, because, for example, SLAM is very relevant to the technologies that autonomous vehicles are requiring now. So if you can build a 3D map of small space by yourself, then so why don't you do that practically as well? So if you already have a huge base map, but if, for instance, a new park is built or new buildings are appeared, then you may not really use or ask the company to build a map for such a small scale change. Instead, you can just drive yourself using your autonomous vehicle and collect data and add the map that you build yourself to the original map. So if you keep doing that, say imagine in 10 years ahead, if you have say 10 million or 20 million autonomous vehicles around the world, and if you can get the sensor data from them on the cloud, then you can build a 3D map everywhere automatically almost every day. So that's what we want to do to circulate. Then we can also publish the data to the vehicle, every vehicle. So this is also a prototype system that we are providing a driving vehicle, the map from the cloud. So this vehicle has a mobile connection, and it tries to download the map when it requires. And if the map is already used, then it can just discard, so that the vehicle only needs to have say a few megabytes of storage space, which is very affordable for a mobile vehicle system. So collecting data from vehicles all over the world then analyze it and build a map, and you can publish this map to every vehicle again. So feedback, making a feedback to every vehicle. So this kind of data circulation is pretty interesting to me because it can build an ecosystem of autonomous vehicles and a 3D map. So this is the main one of the main projects that Nagoya University is facilitating. Yeah. And the rest of the things may not be surprising because everybody is doing the same in different, institute, schools, and so on. So this is tracking of the preceding vehicle by using laser sensor. So this uses particle filters, which you may study in, which you may already have studied. I'm not sure. So we use some kind of probability to recognize who is the vehicle in front of yourself, and it is detecting maybe this is vehicle, and the tracking. And the result of tracking is depicted by a green line. So it can track this vehicle for this demonstration for 30 minutes. It's a pretty long time. We don't use camera. It's the result of tracking from the laser sensor. We don't use camera, just we reproject. Maybe vehicles is here on the picture from laser sensor information. So we don't really use camera, just projecting on the camera. It's surprising because we don't have a camera, but still you can track the vehicle driving in front of yourself. Of course, but we still use camera because the laser sensor doesn't know color information. For example, traffic light, if it's green or red, we need a camera anyway to recognize. But here, we can again use the 3D map information. So we already know where is the traffic light located because we have 3D map information. So we don't have to find out what is traffic signal from this old picture. We don't really have to search for that because we already know when the next traffic light is showing up and where it is located. We already have such information in as a static 3D map information. But still, in order to see what's the color, we need a camera. And of course, object detection can also be supported by a camera. The previous demonstration shows that we can do object detection and tracking by only using laser sensor. But of course, if you have a camera, it can enhance argument, the results, or the accuracy of detection. So that's why we use both sensors, camera and laser sensor, and integrating two results into more accurate detection information. And however, image processing is compute intensive, so sometimes it doesn't finish in a few hundred milliseconds. It may take a second or so. So we use hardware, special hardware, which is called GPU, which is very fast for graphics processing and also other processing as well. By using GPU, then you can accelerate the processing time, actually processing performance by almost 10 times. So if your laptop takes 1 second, for example, to detect a human, but if you use GPU, it can finish in 100 milliseconds. So if detection speed is 10 times different, then you see this different results. So the detection result is the same in both cases because we use the same algorithm. It can both detect human, but because in this case, processing time takes is about a second. So if a second passed, then a human is already moved. So since this is my expertise, I like to make processing performance to be improved by using hardware or sometimes software skill techniques. This may also be relevant to what you are going to study. For example, recently, instead of making a future of the object by yourself, you can just ask the computer to learn futures of the object. So in this case, we use deep learning for detecting the object, detecting vehicles. So we ask a trainer to train what the vehicles look like by themselves. But because the vehicles are pretty futuristic, so sometimes you may not see much difference between kind of deep learning and traditional pattern recognition. But if you want to, for example, estimate which direction the vehicle is moving or what type of the vehicle model, then deep learning may be more powerful to provide you more detailed information. And also, we can do a tracking, not by a laser sensor, but by image processing, so estimating how the vehicles are moving. So we use KLT, it's a Kanade Lucas. I forgot the last name. So, but Kanade Sensei is a pretty famous researcher, used to work at the CMU. So he's one of the greatest professors, which have so many, good results in the literature. In case of deep learning, for example, you need data sets. If you don't have data sets, then you cannot train the model. So we are collecting data to train. For example, how humans are behaving. So this is laser sensor information, and this is camera information, and we also record human data. It's axle, brake, and steering. So if you train them together, what we expect to see is that if you encounter a similar scenario, then the artificial intelligence may be able to tell you, what action is, statistically correct, or even it may be able to tell how you should change the steering or brake axle by, a computer. So, but we are not sure if this is practical yet, because we are still work in progress to still collecting data and training, and to see how the results are. But this is kind of work in progress. But we are expecting to see maybe the computer can just tell you what's the right behavior is against the encountering scenario. So, okay, this is another topic. So since you have two sensors, why don't you fuse them? You don't really have to use two sensors individually. Instead, you can just integrate two sensors together. So this is what you can see from the camera, and this is what you can see from laser sensor. And we are, kind of synchronizing in time and space. And by interpolating between, so there are almost 30 layers, because the laser sensor is scanning by 32 layers. So we can interpolate the sensor information to make more image-like information and putting them together. So since the picture doesn't have distance information, but now you see that the red area shows it's close to you, and the blue areas, it's far from you. So now the camera information has a distance information. And if you do this, say, when you detect the vehicle, then you can see how far it is from yourself. This is often called reprojection. So when you detect the vehicle on the camera, then you can reproject the position of the detected object to 3D coordinates. Because two sensors are integrated now, they know each position each other. So by doing this fusion, then the detection is supposed to be more accurate rather than just using a LiDAR, laser sensor information. So, okay, now you can detect objects and you know where you are driving. Now what you have to do is to make a plan for the driving. And because a vehicle has constrained dynamics, it cannot, for example, make a sharp turn, especially when you are driving at high speed, because it's dangerous. So perhaps only 6 ways of motion could be taken by a vehicle. So under this constraint, we can make, for example, a possible path which the vehicle can take from the current time. And you keep computing what path could be taken by the vehicle in 3 seconds, for example. Then in this scenario, in this demonstration, because there is no vehicle in front of yourself, you don't really have to take a different path. But if you encounter some parking vehicle, then maybe you can change a different path so that it can avoid the parking vehicle. And again, let's come back to 3D map information. So when you make a plan of your vehicle, now 3D map is going to be useful again because it has a lot of road information, especially the 3D map knows when crossroad is appearing and precisely which location. So the vehicle already knows here is a crossroad, so let's be careful. And the next crossroad is appearing. And since something is on crossroad, so by high probability, this is a human. So it can put a high priority, object. And now it knows the next crossroad again. So collecting what I have demonstrated so far, then it may not be able to drive like a human, but if you give the vehicle a route to the destination, if the vehicle follow that route, then basically we can do autonomous driving. And if something shows up, then we can just stop. And if it's removed, then we can restart. Or if just a parking vehicle, then we may be able to detour. The next stage is maybe to make it like a human. If something is showing up suddenly, then don't just stop, but it sometimes may have to take another decision to avoid or so on. That's what we are going to work on the next project. So everything that I have demonstrated so far is actually open source. So if you want to try to use the software, you can just download it from our website. Since we don't have English version of the manual, it may be difficult, some of you, to understand how it can be used. However, at least source code is open, so everybody can use it. Okay, let's wrap up. So I talked about how to build an autonomous vehicle from scratch. So first you need kind of hack to the vehicle in order to make an interface between the computer and vehicle. But after you make such interface between them, then now we can provide a platform, software platform, that can allow you to build an autonomous driving system from scratch. Actually, we have more and more users of this software, and they are not just using our function. They're actually adding their favorite function to our platform to improve the system by according to their specification. So we are happy to be used in such a way, because this is not production quality. This is open source software. This is a basement for a research project. So somebody downloads it, and we still appreciate if they just use it, but we appreciate more highly if they can improve the software and make some feedback to us. That's what we are trying to achieve right now. Okay, so it was quick, but this was a brief introduction of my research project, and I talked about how we can build an autonomous vehicle from scratch. And only a few pieces of information may be included in my presentation about which is relevant to what you are studying, like particle filters or deep learning or collecting data and analyzing and so on. Okay, so thank you very much.